This next topic we're going to talk about is health demand, the demand for healthcare. Now, we've already started talking about health demand and how it's a pretty complicated thing, how it's got a couple of different individual decision makers that are part of it. What we want to do is we want to dive a little bit deeper into some of the economic tools to thinking about demand, and then head back and say, okay, in the context of health, what's a more sophisticated look at the demand for healthcare? But again, we're thinking of the demand for health as being a derived demand. Um, you go out and buy medicine, you can exercise, you can take care of yourself, you can buy healthy food or pills or medicine, and all of those things together produce health. You value health, you want health, you have a demand for health. That's the general context that we're talking about. But again, before we get there, we want to start and revisit some basic consumer demand concepts that you may have seen in microeconomics, or maybe you didn't, depending on who taught it to you, and depending on how long it's been, you may not remember some of these things. But we're going to start out with a basic review. We are going to begin with a simple story. In our simple story, you can buy either apples or starfruit. Do you all know what starfruit are? I don't know if they have starfruit down at Community Market, but they're these nice little sweet fruits and apples. Everybody knows what apples are. So we're going to make some unrealistic assumptions real quick. Let's assume that you have $200 of income, and let's also assume that each individual apple costs $4. That's unrealistic. Let's also assume that each individual starfruit costs $8. It's also unrealistic. But what if that were true, right? We can do some thought experiment and ask, what if those were the correct values of income and prices that you had? Okay, so the big picture is we want to start and think about the constraint side of consumers for a second, right? Remember that economics is about making choices under scarcity. We want to first focus on the scarcity. You have a scarce amount of income. How can you spend that income? The budget constraint is a concept that's going to show us how are all the possible ways that you could spend your income. So we can real quickly think about this. Yeah, if you have $200 of income and apples cost $4 a pop, a little bit of math tells me that you could, if you wanted, you could buy 50 apples. But that's again spending all of your money on apples. That's one way that you could spend your money, but alternatively, you could take your $200 and you could spend your $200 on starfruit. Those costing $8 a pop, sounds like you could buy 25 starfruit, right? That's another possible thing that you could do with your income. The budget constraint is a concept that shows us all the different possible combinations of what you could do with your income. So I have this little equation right here. If I direct your attention to this equation, does it make sense that this equation is describing your budget constraint? What we have here is, on the left, you have your $200 to spend. Assuming that you spend all your money, which is a probably good assumption, you can either buy apples or starfruit. This equation describes all the different possible combinations of apples and starfruit that you could buy, right? $4 a pop for an apple and then how many apples you buy, plus $8 a pop for a starfruit, and how many starfruit you buy. Notice, right, that we've got an indirect relationship between the amount of apples you could buy and the amount of starfruit you could buy. If you're going to buy more apples, the only way in the world that's possible is buying less starfruit, assuming that you don't have additional income yet, right? So this equation describes all the different possible combinations of what you could buy. That is, this equation is the budget constraint. What we want to do is we want to tell the story about consumer behavior in a graph, though. So this graph may look a little bit different than traditional demand that you're familiar with, right? Usually when I talk about the demand for a product, we've got price, we've got quantity, and I think of demand as a downward sloping line. That's true, but we're not there yet. We're going to build some of the tools that are behind where that demand curve comes from. So let's think about a world where you could buy either apples or starfruit. I want to measure apples and starfruit on my different axes, right? Horizontally, I'm measuring how many apples you could buy. Vertically, I'm going to measure how many starfruit you could buy. So could we take this equation and plot it in this space? Well, actually, we've already done half of our job, right? Because we could think about our two endpoints, our two extremes. Again, if I spend all my money on star fruit, how many star fruit could I buy? I could buy 25 star fruit. Let's arbitrarily throw the number 25 right here. Let's arbitrarily throw the number 50 here for apples, right? I don't have any scale on that, so those are totally reasonable numbers. If I just connect spending all of my money on star fruit with spending all of my money on apples, that line right there is what I want to call my budget constraint. It shows me all the different possible combinations of what I could spend my money on. And again, if I want to buy more apples, I can do that, but the only way I can buy more apples is if I buy less star fruit. Or what I really want to do is get an equation that describes this guy, right? So whereas you may be familiar with your old traditional y equals mx plus b form of an equation, right? That's when we've got x and y and we've got some line like that, but we don't have that, right? Instead of y, we have star fruit. So we want to rearrange this general equation for a budget constraint so that it gets the thing that we're measuring on the vertical axis, that is star fruit, alone on the left-hand side. Little bit of algebra tells me that I can do 8SF equals 200 minus 4A, right? Double check in your mind that you could algebraically just rearrange that thing. And then if I divide through by 8, an equation to describe this line, SF equals 25 minus 4 divided by 8, 0.5a. That's an equation that describes the budget constraint in this space. I would refer to this space as output space because instead of looking at prices and quantity, we're looking at output of star fruit and output of apples. Or I could call it product space because we're looking at the products of star fruit and apples. In that product or output space, this is an equation to describe your budget constraint. And right, it's got some properties that we're not all that surprised about. The vertical intercept corresponds to the 25. That was, if you were going to spend all of your money on star fruit, how many star fruit could you buy? But there's something else going on here. What about this negative 0.5? That negative 0.5, where did it come from? It came from negative 4 divided by 8, which was a ratio of the two prices, right? The slope of this equation, the slope of the budget constraint, is what we'd refer to as a relative price. The relative price of a good is the price of a good relative to the price of other goods. The ratio of these two prices, that is relatively the price of star fruit in terms of apples. So what we have here, right, that relative price, that slope of the budget constraint, it tells me the trade-off that I face in terms of my resources. If I have, let's say, $8, I could use my $8 to buy one star fruit, or I could use my $8 to buy 2 apples. Yep, with that $8, I've got a 2-to-1 trade-off. Or, if I want to think about it in terms of star fruit, it's a 1-to-1/2 trade-off. Either way, 2-to-1, it's the trade-off that I face in terms of consuming my goods. Before we leave this, I want to do one other quick thought experiment. This is a budget constraint based on 2 assumptions. The assumption was I have $200 of income and these are the prices of my goods. But can we think about how would the budget constraint change if the prices changed? Or how would the budget constraint change if there was a change in income? Let's consider an increase in the price of apples up to $10 a pop. $10 a pop, what's that going to do to this budget constraint? Will it have any impact on my vertical intercept of 25? It shouldn't, right? My vertical intercept, in this case, referenced spending all of my $200 on star fruit. Yep, if I'm spending all my money on star fruit, it shouldn't matter that the price of apples went up. However, My vertical intercept, my old vertical intercept or horizontal intercept of apples used to be 50, but now if the price goes up to $10, what happens? Well, if I want to spend all my $200 on apples, and apples are $10 a pop, now, geez, that's terrible. I can only spend $20, or I can only buy 20 apples. My budget constraint is going to rotate in. When I add an increase in the price, it's going to change the slope of my budget constraint. Remember, we also said a second ago originally that the slope of the budget constraint were relative prices, and for this, the original example, we had the slope being -4 divided by 8. Now, with the new prices of apples, that's going to be -10 divided by 8, which is -1.25. A much, much, much higher relative price, a much, much steeper slope. That's exactly what this budget constraint looks like. It looks like the slope became steeper. When the price of apples went up, the slope of the budget constraint changed. So, that's what happens if the price, or I could say more generally, that's what happens when the relative price of my goods that I want to consume changes. How about the other assumption that we made about the value of income? What if there is a change in income, right? What if the amount of income you have goes from $200 up to $400? Again, I like thinking about these two intercepts. The original intercept on starfruit was 25. The original intercept on apples was 50. But now, what if you have $400? If you have $400 and starfruit are their original price of $8, now you can buy 50 apples. You could buy twice as many. If you have $400 and we are back to the original price of apples at 400, now you can buy twice as many, somewhere way out here at 100. And that, oh boy, if I was trying to be really careful with that, I would draw it as a line that looks something like this. That's mostly a good line. Mostly a good line. Straight line, as you can tell. That is further out from the origin. I would want to describe that as that budget constraint being further out from the origin. But notice, right, when we have an increase in income and there is no change in price, the slope of this guy is unchanged. We have a parallel shift out from the origin when we have an increase in income. Right? So we can think about two different households with two different levels of income. Their budget constraints are going to look like two different lines. The household with the higher amount of income is going to have the budget constraint that's further from the origin. A household with a lower amount of income, their budget constraint is going to be closer to the origin. All of this is describing what consumers face in terms of their constraint of resources. If they've got some income, if they've got some resources, this tells me all the different ways that they could possibly spend it. I really want to think of the budget constraint as falling on the cost side of the story. Next, we're going to turn to the benefit side of the story. Moving from the cost side of the story to the benefit side of the story. Why would you ever want an apple? Why would you ever want a star fruit? It's because they're enjoyable to eat. You get satisfaction out of consuming those goods, right? We had talked entirely about what do you have to give up in order to get a good, but why do you ever want a good? Because there are some benefits aside to that. We're going to introduce this concept of utility and indifference curves here. To an economist, utility refers to satisfaction. Sometimes we refer to utility as being a measure of happiness. It's okay for us to just think about how satisfied you are with things. In general, we need to make some underlying assumptions about what people's satisfaction is, or what people's happiness is with different goods in the world. Real quickly, this isn't a major point, but I did want to point this out. When we think about goods in the world, we're going to make these 4 assumptions about utility. Number 1, that there is a completeness to utility. That is to say that for every possible set of goods that exist in the world, you know how happy or how satisfied that combination of goods would make you. More is better. We're going to make an assumption in here that for goods and services, that the more you have of them, the more satisfied you are, the happier you are. In general, I think that's a pretty okay assumption. The more you have of stuff, whether that be the more you have of money, or the more you have of automobiles, or the more you have of food, or the more you have of your free time, that the more you have of all of those things, the better, the happier you are. We're going to maintain that assumption. Transitivity is a minor assumption, but it basically means if you prefer A to B and B to C, then it must also be that you prefer A to C. That is, if we're thinking about apples, bananas, and cherries, if you prefer apples over bananas, and you also prefer bananas over cherries, then it must also hold that you prefer apples over cherries. Convexity. Convexity refers to the amount that some combination of goods is better than an extreme amount of goods, which is actually the way that a lot of consumers actually behave in practice. So underlying the idea of utility are these four assumptions. They're not hugely important, but I did want to throw them out there real quickly. In general, utility, satisfaction. If we're thinking about apples, the relationship between how many apples you have and your level of happiness with apples, I'm going to assert that more than likely your utility looks something like this. That is, the more apples you have, yes, the happier you are. However, those first few apples that you consume, the additional happiness you get is pretty large. But as you consume a larger amount of apples, you're happier, but at a diminishing rate. Your happiness goes up, but at a much smaller rate than how much your happiness went up for the first few apples. And we can think about this property of the diminishing marginal benefit of goods being pretty ubiquitous, right? You go to a all-you-can-eat pizza, the first piece of pizza really good, the 10th piece of pizza not so good anymore. That's true. We're going to assume that's true for most goods. What does that actually look like? If we assume that that's true for apples, and alternatively I could say that's also true for starfish, what would that look like in functional form? I've got this function right here that might look a little complicated, but it's not too bad if we parse it apart. Your total utility, that is the total amount of happiness you have, it's equal to 4 times, let's see, the number of star fruit you have raised to the 1/2 power times the amount of apples you have raised to the 1/2 power. So do you remember x squared and what that thing would look like, right? We take x and we square it. This is raising star fruit to the 1/2 power. In essence, this is the same thing as taking the square root of a value, of a variable. This property, having a 1/2 squared power, I'm only doing that because its picture looks something like this. The picture of a raised to the 1/2 power looks something like that. So if we have an equation that's going to tell us total utility, we can also introduce this concept of marginal utility. Marginal utility, whereas total utility tells us our total amount of satisfaction, marginal utility, or MU, simply tells us additional satisfaction, or additional utility, or additional happiness. Marginal utility is how much additional happiness additional goods cause you, or bring you. So like we mentioned a second ago, the more you have of a good, the smaller marginal utility is. Marginal utility is positive, but at a diminishing rate. We have the property of diminishing marginal utility. Well, we're going to hop to calculus just real quickly for a second, and the word marginal means additional. Whenever you see it, think additional, or if you're thinking calculus, think derivative. And if we think about taking the derivative of this utility function, we've got more than one variable, so we're actually taking a partial derivative. The marginal utility of an apple, that is to say, how much additional happiness I have from an additional apple, is the partial derivative of utility with respect to apples, which, if you remember a little bit about derivatives, right, we take a derivative by bringing the exponent down and multiplying it in the front. So 4 times the 0.5, 2. If I'm doing a partial derivative, I leave my other variables exactly the way they were, and then what I am taking the derivative with respect to, I reduce the exponent by 1. So 0.5, let's make that clear, 0.5 minus 1 is negative 0.5. That equation is an equation that describes the marginal utility of a good. Notice, as A gets larger and larger and larger, the size of marginal utility, it remains positive, but it gets smaller and smaller and smaller. This step that we just went through about finding the marginal utility, don't worry about it if that didn't click with you. It's not a major part, but I did want to include it as part of this discussion. So we've got the marginal utility of A. We've got a utility curve that has the property of diminishing marginal utility. But that's telling the story entirely in terms of A. What I want to do is I want to tell a story about both apples and star fruit together. So I want to jump back to my world where I'm looking at the relationship between star fruit and apples. If I do that, I've got to introduce this concept of an indifference curve. An indifference curve is a curve. It's a line. We're going to define it as an equation, but it's a single line that tells me all the different possible combinations of star fruit and apples that produce the same level of utility. Here's my way of expressing it in an equation. I've got really similar to what I had before, my utility function, but now instead, the only difference that I have is this little bar over the u. When I put a bar over a variable, I can mean two things. In statistics, it means I'm taking an average. But if I'm talking about mathematics, putting a bar over it can mean let's hold that thing constant. Let's have that be one single value, and that value is held constant. So what we're doing here is we're holding constant the amount of utility. Utility will be the same. Happiness will be the same. This equation tells me all the different combinations of star fruit and apples that make me the same level of happiness. Now notice, if we jump over here, we've got a couple of different indifference curves. These indifference curves are, I calculated some values, right? What if your utility was 312.5? Or what if your happiness was 370? These lines show me all the different possible combinations of star fruit and apples that produce utility of 312. And notice there's also an indirect relationship with those. Hopefully that's not a surprise, right? If I take away some star fruit from you, you're not going to be happy. But could I get back to your original level of happiness? Sure I could, by giving you additional apples. There's this trade-off between star fruit and apples in terms of how happy they make you. And we've got this utility here, this indifference curve right here, is based on a higher level of happiness. Does it make sense that a higher level of happiness is going to be further out from the origin? Indifference curves that are further from the origin represent higher level of happiness? Sure, that makes sense, right? Because for a given amount of star fruit, which is going to make you happier, having this amount of apples or this amount of apples? Clearly, more apples makes you happier. And alternatively, we could say, for a given amount of apples, which level of star fruit makes you happier? This amount of star fruit or this amount of star fruit? Nope. Because of our assumption of more is better, more star fruit makes you happier. So right, we've got that indifference curves that are further from the origin represent higher levels of happiness. Real quickly, if we jump back to our previous story, higher budget constraints represented higher levels of income that we would need, right? In essence, I'm thinking about those as being higher costs are associated with higher budget constraints. Budget constraints that are further from the origin, those represent more expenditures, but higher indifference curves, or indifference curves that are further out from the origin, represent higher levels of happiness. Real quick, let's think about the shape of those things. Notice these indifference curves, they're not, oh look, there's a bunch that are hidden over there that I totally forgot about. There are some indifference curves that are, so we've got some indifference curves with a very particular shape to them. Notice the shape of these indifference curves. It starts out, it's a negative number all through, or sorry, it has a negative slope all throughout. But notice that the slope at here is a very, very, very negative number. And then that number gets less and less. The slope gets less and less negative. It maintains its negativity all throughout, but it gets closer and closer to zero. Slope starts out very, very high and then gets lower. It's negative all throughout, but starts out high, gets lower. Just like the slope of the budget constraint being a pretty meaningful thing to us, we can define the slope of the indifference curve. The slope of the indifference curve is this concept called the marginal rate of substitution. The marginal rate of substitution tells us our trade-off in terms of our happiness between goods. And I'm going to assert some things and then not go through a whole bunch of math. The marginal rate of substitution for an indifference curve is the ratio of its marginal utilities. So if I'm looking here with looking at starfruit and apples in this context with these two outputs, the marginal rate of substitution is the marginal utility of apples over the marginal rate of starfish. So what we did earlier was we came up with an equation that described the marginal utility of apples. Could we also come up with an equation that described the marginal utility of starfruit? We could, but we're not going to. If we took the ratio of those two equations, we could do that, but I'm going to skip over that math and get us all the way to the finish line and say the marginal rate of substitution for this particular particular utility function is equal to SF divided by A. Now, if you want a little math challenge, set up marginal utility of A, figure out marginal utility of starfruit, take their ratio, you're going to end up with this. In general, if I graph out the indifference curves, if I graph out the curves of this, the slope of these lines are equal to SF divided by A. That is, the slope of this equation is going to be equal to this marginal rate of substitution. I want to go through a little thought intuition as to why that makes sense, right? If I've got my indifference curves, we just said a second ago that indifference curves, their slope always negative, right? And that's where the negative comes in. Always negative, but starts out at a very, very, very negative number. It's a very large negative number. And then it gets smaller and smaller. Marginal rate of substitution, the slope, marginal utility of apples divided by the marginal utility of starfruit. Reduces down amount of starfruit divided by apples. So again, if I think about this point right up here, I've got a whole lot of starfruit and I've got a very small amount of apples. If I think about my ratio, a very large number in my numerator divided by a very small number in my denominator, it's going to be a large number. As I move down my indifference curve, the slope still negative, but becomes less negative. It becomes closer and closer to zero, so that by the time I get down here, it's not zero, but it's a number very, very close to it. Well, let's see. At this point right here, I've got very little starfruit, but a whole bunch of apples, right? Again, thinking about my ratio, a very small number in my numerator and a very large number in my denominator. Yep, the slope, the marginal rate of substitution, is going to be low. Again, if I'm thinking about moving from a point where I have a whole lot of starfruit and very few apples to a point where I've got a whole bunch, or a very, very small amount of starfruit and a whole bunch of apples, notice that for starfruit, when I have a bunch of them, the marginal utility of starfruit is going to be a pretty small number, right? Additional starfruit gives me very little additional utility, and also taking starfruit away reduces my utility by a very small amount. Whereas if I'm going to add more apples, but I don't have that many apples, starting out with a small amount of apples, the marginal utility of getting apples is very, very large. right? We can also think about the ratio of this thing, the marginal utility of apples, being a very, very large number because having very few apples, additional apples, really valuable, divided by a smaller number marginal utility of star fruit, because if I've got a bunch of star fruit, adding one or taking one away isn't going to change my utility all that much. All of this is a story about the benefits that consumers get, right? You consume goods because they make you happy, but you've got a limit to how much you can consume. So if you're going to consume some apples, they produce some happiness, but it means you're going to have to give up some star fruit, and giving up star fruit makes you less happy. So how many apples should you consume? How many star fruit should you consume? The correct amount of apples and star fruit that you could consume is going to combine the idea of a budget constraint with the concept of an indifference curve. That's where we're going to head next. We want to consider what an optimal consumption bundle would be. That is, what's the right amount of apples and star fruit to buy? By optimal or right or best, we're going to refer to, given your income constraints, what level of consumption of apples and star fruit is going to produce the highest level of utility for you. That's actually one way that we can describe the term optimal. But there's another way that we can think about optimal. If you want to reach a certain level of happiness, what is the optimal, the best combination of star fruit and apples that get you to that level of happiness but require the smallest amount of income? That's actually the two different pictures that we have here. So we're going to consider the optimal, the good, the correct amount or combination of apples and star fruit as being points A. And I'm going to walk through why points B and C are not the optimal combination of star fruits and apples. But they're wrong, they're not optimal for different reasons, right? So we can consider this first combination of apples and star fruit right here, and this other combination, B, of apples and star fruit right here. We could ask the question, what do they have in common, and how are they different? Well, what I can observe, because both A and B are on the exact same budget constraint, what I know about those two combinations is that the income that it would take for me to acquire those, or the cost of buying those combinations of output, are the same. Those two combinations will cost me the exact same amount of money. It takes the exact same amount of income to get to those two different combinations. But combination A is better. Combination A is optimal in effect. Why? Combination A is optimal because it is on a higher a higher indifference curve. Indifference curves that are further from the origin represent higher levels of happiness. Yes, A and B cost the same amount, but A creates a higher level of utility than B. That's why A is considered an optimal combination. They spend the same amount of money, they cost the same, but A produces a higher level of happiness. Whereas, what do we know about, not A and B, just kidding, A and C on the right here? We can consider A and C. A combination of apples and star fruit produce a certain amount of happiness for a different cost, and C also produce a certain amount of happiness for a certain cost, or it takes a certain amount of income to get there. What do we know about A and C? Well, what we know about A and C is those are two combinations of output that are on the same indifference curve, right? Their indifference curve is the same. What does that mean? That means I am equally happy between both of them. I am equally satisfied with combination A and combination C. Their utility is the same. However, why is A considered a superior combination of output? A is on a lower budget constraint than C. C is on a budget constraint that is further from the origin. Remember, for these budget constraints, Budget constraints that are further from the origin represent higher income. We need more money in order to get to those higher budget constraints. Those higher budget constraints require more cost. So yes, they produce the same level of happiness. In a sense, their benefit is the same, but A is so much better to C than because A has a lower cost. Or I could say that A takes a lower amount of income to get there than C. Different reasons why A is superior to B and C, right? In the first, same cost, but A produces a higher benefit or a higher level of happiness. Same happiness, but A is superior because it gets there at a lower cost. Both of these are considered optimal. They're just optimal in a different way. What I want to ask, though, more generally is, okay, if I have a given budget constraint, how do I know where the optimal level of consumption is? What I need to do is look at the slope. Notice that at that first point, that first non-optimal combination, the slope of the budget constraint is different than the slope of the indifference curves. At that point, those two curves intersect each other. Whereas at my optimal combination here, the slope of the budget constraint is equal to the slope of the indifference curve. The word I have for that is those two lines are tangent to each other, right? Tangent versus intersection. A tangency implies that two lines share the same point and have the same slope. If I have an intersection and not a tangency, it's not the optimal point. But notice that this story about slopes is the exact same condition for optimality on the right. Optimality on the right said we've got the same level of happiness, but different costs or different levels of income required to get there. But notice, same thing about the slopes. For the non-optimal combination, the slope of the indifference curve is different than the slope of the budget constraint. But at my optimal combination, the slope of the indifference curve is equal to the slope of the budget constraint. It looks like regardless of how I conceptualize the idea of optimal, the condition is a tangency between my budget constraint and my indifference curves. My budget constraint, the slope of my budget constraint shows me the trade-off in terms of buying stuff. My indifference curve, its slope, the marginal rate of substitution, shows me the trade-off in terms of the benefit I get from goods.